Okay, sorry about that. We're just going to do that last part over again. So this is part F, where x over, where r over x is much, much less than 1. So x is approaching infinity and r is approaching 0. And you're very, very far away from the disk, right? Okay, cool. So let's copy down our Ex is equal to 2 pi charge density k 1 minus x over square root x squared plus r squared, because that's Ex in limit. And we want to use the approximation that's on our reference sheet, which is 1 over square root of 1 plus x, which is approximately 1 minus x over 2, right? For an x that is much, much less than 1. So here, our x, use r over x as x. Really, it's going to be r squared over x squared, which is fine because r squared over x squared is much, much less than 1. Obviously, if r over x is much, much less than 1, they'll be the same. They'll both be much less than 1. So we can just massage our equation again to get this kind of expression, and to get this kind of expression, but just using this for x, so that we can put this in and we can figure out why this is meaningful, what this case means, where r over x is where x is much, much farther away to the disk, and in this case where you can use this linear approximation because of that, what that would mean for the electric field formula. So let's pull out an x over square root of x squared time, right, which is really 1, which is really going to be 1 over square root of 1 plus r squared over x squared. Yeah, so that is going to be the case. And then, and then we are going to this becomes 1, right? So that simplifies. And then we have 2 pi charge density k, 1 minus, and then let's replace this with our expression, because this is similar to this, so using this for x, so we can use 1 minus r squared over x squared divided by 2, so 1 minus r squared over 2x squared, right? Which is equal to 2 pi charge density k, right, times 1 minus 1, which is 0, and then negative r squared over 2x, which is going to be positive r squared over 2x squared, over 2x squared. That's what I meant before. And then we have these 2's that cancel out, so you get pi charge density k r squared over x squared, and we know that q naught is equal to charge density pi r squared, which we can see all those things over here. So we have E is equal to k times q naught over x squared, which is just as we expect, that if you're really, really far away, then a disk is going to look like a point charge, right? Which is what we discovered earlier when we saw that the voltage was really, really far, when we saw that the voltage of a point charge came out of this expression when we were finding previously that x was really, really far away from the disk. Now we want to find that for the electric field, that also looks like similar, that also looks to be the case using this approximation. So this is true because this is the formula for a point charge, right? This is where our r is actually going to be x in this case, and q naught really means that this charge density times the area of the disk, and then we have this 1 over that, which is k. So this is the same as a point charge, and this makes sense because it's so far away that the disk's size will no longer matter because it'll be just a small point. So the radius the distance that you are from it will matter, but the radius won't matter anymore. And this is our expected result. So that is the answer to this Chordoso problem.